Okay, welcome everybody to the Tunneling in QFT online series. We are resuming after a short break, and I should also welcome our new co-organizers. So we've been running this series now for a while, and we are very happy that we have now Wenyuan, I, and Benoit Laurent, who are joining the organization of this series. So welcome and thank you for the efforts.
Hello, everybody.
Hey,
Hello.
hi, Wenyuan.
Hi, happy to be here.
Yes, thank you for joining. So this is now almost 2 years that the series has been running. The next talk will be in December 11th. It's going to be Peter Athron, and then in January we'll have Jorinde van de Vis. You can check out all the talks on our Indico, and of course you can see all the previous ones together with slides, and we have a YouTube channel where all the talks are, so you can go check them out or send the link to your students or whatever. Great. So today we have Jose Espinosa from IFT Madrid, and Jose is an expert on these topics, tunneling in particular. He's been working on a lot of interesting things like standard model vacuum stability, Higgs physics, phase transitions in general, spontaneous symmetry breaking, SUSY, and general BSM. And he's developed a formalism of tunneling potentials, which is rather interesting. And even though he's been working on this for a long time, it seems that there's a lot of surprises still left in this field, no? And he's going to talk about them today. So please, Jose, thank you for joining us.
Thank you, Micha. Thank you for the invitation to give a talk in this very nice online seminar series, which I really appreciate all the effort you are putting into it. So it's for me a honor and a pleasure to give one of these talks. And I say it's a pleasure even though I hate giving online talks, especially because I feel sometimes that I'm talking to a wall. So I would encourage people to please interrupt as soon as you don't understand anything so that nobody gets lost. And if I don't finish the talk, it doesn't matter, at least you understand what I'm talking about. So Micha asked me, the organizers asked me to give a talk on pseudo-bounces. So this is what I will talk about today. And wait. I don't. Oh, okay. So the goal will be just to explain to you what pseudo-bounces are. And I will use them to explain these kind of surprises that one can still find in vacuum decay, as Micha was saying, right? So I'm going to do this in basically two different parts. First, I will introduce these pseudo-bounces using the standard Euclidean approach, which is more familiar to everybody, and that's a better way of understanding what these guys are. And then I will use the same approach just to discuss these applications and these surprises. And then in the second part of the talk, I will just use the tunneling potential approach that gives a different view on pseudo-bounces, and in fact makes them like more serious in a way that you will see. So first part, just the Euclidean approach. We all know the problem that is at the heart of this seminar series. This is the problem of forced vacuum decay, right? So I will just consider a potential no gravity, just a simple one field potential with a forced vacuum at 5+. You can take this to be 0. Energy density, you can also set at the forced vacuum to 0 without loss of generality. And then we know that because the theory is quantum, then field fluctuations are going to fill this deeper part of the potential. And in particular, they can create a bubble of this deeper phase that can destroy the homogeneous forced vacuum, right? So this is tunneling process between these two states. The initial state is just the homogeneous forced vacuum, and it tunnels to this bubble. It has this second state has the same energy as the initial one, so that energy is not violated during the tunneling process. And once this forms, as I said, this expands and destroys the forced vacuum. This can happen anywhere in space, so we are interested in calculating the rate per unit volume. And if the forced vacuum is sufficiently long-lived, then this is going to be exponentially suppressed. And we are interested in calculating this exponential suppression, this exponent here. This is the tunneling action is an action, so in principle it has the dimensions, but for the rest of the talk I will set h bar equal to 1, so this will be just a number. And you can think of this number as telling you how expensive it is to construct this big semiclassical bubble, okay? So this is an interesting problem that was, of course, solved long ago by Coleman in a very elegant way. He went to imaginary time, so this everything will happen in four-dimensional Euclidean spacetime. And in particular, for the description of this tunneling in vacuum decay, you have to find a configuration in this Euclidean spacetime, which is called a bounce. He also proved that this bounce has an O4 symmetry. And so it just depends on the coordinate, which tells you what is the distance to its center, okay, phi b of r. And this field configuration extremizes the Euclidean action, which if you use O4 symmetry is just written as this simple integral. And notice that the potential has an unusual positive sign in front because we are in Euclidean signature, right? So because the bounce is an extremal, then it will be a solution of the Euler-Lagrange equation that you get from this action when you vary the field, and that I brought here, okay? Everybody knows this in this similar series. So the boundary conditions that this bounce has to satisfy is first, it will take some value phi 0 at the center. This phi 0 probes the deeper part of the potential, as I said. And the slope at the center has to be 0 so that you don't have a singularity from this term here, okay? And as you go away from the center of the bounce, then the field will relax to the false vacuum, okay? So the profile will look something like I showed here pictorially, okay? So once you find this numerically, typically, you can plug it in the action, and then the tunneling action will be given by the difference between the action of this bounce solution minus the action associated to the initial false vacuum state. If you choose the energy density of this state to be 0, then this is going to be 0 anyway. So one more word I want to say about the bounce action. You can write it as the sum of two terms. One is the gradient term, S sub k. The other one is the potential term, S sub b. And then you can prove that the contribution from the kinetic term is going to be twice the total, and the potential is going to be equal to minus the total, so that you end up getting the right result. And you can prove this in a very smart, simple way, just looking at the form bounce, in which you multiply the radial coordinate by some constant a. And because the bounce is a stationary point of the action, then you have this relation that the derivative of this thing with respect to a at a equal to 1 is 0. And doing that, you can prove this relation that I brought here. And in particular, this tells you that you can write the total action as just an integral over the kinetic term, dividing it by 2. Okay, this is well known, but it will be useful later on, and that's why I remind you of it. Okay. Another thing that is very well known is how to solve this problem numerically, and again, I will go through it because it will be important for the discussion that will follow afterwards, right? So you look at this this equation as describing the motion of a particle. The field will be interpreted as the position of a particle that is rolling down the inverted potential, inverted because it's here the positive instead of the negative sign, and you take r to represent time. So you have the motion of this particle on the inverted potential, and this motion has a friction that depends on the time and depends on the velocity of the fields, okay? So to satisfy the boundary conditions, what you have to do is just to pick a point from which you will release this particle with 0 velocity, and the idea is that at infinite time you have to stop at the false vacuum, which is now a maximum. Okay. Now, if you start very close to the true minimum, which is this maximum here, then the field will spend a lot of time near it, and then the friction will just disappear basically, and then you will overshoot. The field will roll beyond the false vacuum. Okay, so you get this green curve that overshoots your goal. If you start very low, then the opposite will happen. Friction will make it impossible to reach the false vacuum, and then you have an undershoot, okay? This is the red line. And by continuity between these two extreme cases, then you will find a spot, a sweet spot that will give you the bounce that you are looking for, okay? So it's very easy to construct a numerical algorithm to do this. Basically, it has to tell your code that if you find an undershot, then increase your field from which you shoot. If you find an overshot, then decrease it, okay, until you find this sweet spot. So this is the standard story, but sometimes you find surprises like potentials that do not admit the bound solution. So to explain how this can happen, let me just start with a very simple potential, which is the negative quartic potential, in which you have actually an infinite number of solutions, but it will be useful to construct a potential without a bounce, okay? So it is well known that for this potential has a very interesting property, and it means that when you're looking for this release point, this sweet spot, it turns out that any value is good. No matter from where you release the point, the rolling particle, it will always end up at the false vacuum at the origin. Okay, so this phi zero, this sweet spot is arbitrary. Anything is good. Now, once you calculate it for any value of phi zero, the bounce, then you can calculate what is the action, and you find that this action actually is independent of the value of phi zero. Okay, so these two properties are in fact derived or follow from the scaling invariance of the potential. Okay, so the first one, for instance, you realize that phi zero has dimension of mass, so there is no way that you can find a formula for this in terms of the parameters of your potential, because there is no mass here that could give you a formula for phi zero. For the action, something similar happens. The action, as I said, is just a number, and therefore there is no way that phi zero can appear in the formula for this action, because you cannot counterbalance the mass dimension of phi zero with anything else. Phi zero is the only mass dependent term. Okay, so that's the explanation for these two nice features. Now I'm going to use this potential to construct another potential that has no bounds, and is the following. So for positive values of phi, I will just take my potential to be minus the quartic, okay, the one I explained before. But for negative field values on the left, I will just construct some false vacuum here, okay, at some phi plus. And then I'm interested in calculating what is the decay rate out of this false vacuum, okay? Sorry. So to calculate this rate, I invert the potential and I look for some release point that will end up on top of the false vacuum. But because of what I explained before, no matter from where you release your particle, you will always end up at this point phi t, okay? So in other words, no matter from where you start, you will always find undershots. And this means that there is no bounce. This potential has no bounce. Some people interpreted this as meaning that there is no decay, but of course this does not imply there is no decay. Quantum fluctuations will probe what is happening beyond this barrier, and for sure you can find a bubble with zero energy that is going to describe the decay of this out of this false vacuum, right? But then if there is no bounce, how do you calculate this decay rate, and what are the field configurations that dominate this decay, right? So pseudo-bounces are precisely the field configurations that will explain how will drive this kind of decay when there is no bounce. All right. So this is how the Euclidean profile of this configuration looks like. What you do, you remember, you have every try that you try is an undershot. So in order to cure this problem, what you do is just you keep the field fixed for some time, for some distance Ri. This you can interpret as a waiting time to decrease the friction so that you avoid an undershot. And then you tune this length so that at the end of the day, when the field, you let the field roll, evolving with the bounce equation of motion, it will end up at the right force vacuum, okay, when R goes to infinity. This is what you do, okay? So what is the action for these pseudo-bounces? Well, let me start with the action when you only have this negative quartic. As I said, this is constant. So you have a flat direction in configuration space for the action, okay? No matter where you start, you always get the same. And now what I'm doing when I included this other minimum here is I was breaking the scale invariance, and now what I have is that this flat direction is lifted. I could get the same effect if I break the scaling invariance with a master. Okay, I was using this other construction just to explain the effect, but if you do the same with this master, you always get undershots, and you will have the same kind of behavior. You will have pseudo-bounce solutions that will lift up this flat direction. And so you see the fact that there is no bounce is due to the fact that the minimum of this curve is pushed to infinity. Okay. So you end up, instead of a flat direction, you have a sloping valley. Okay, for your action.
Hello.
There are questions? Yes.
Yeah. Yes, I have a question. So,
Good.
so for the pseudo-bounce, so does it follow from the equation of motion, or how did you construct it?
So first, you have to choose this waiting time. You have to tune it so that when you release the particle, you will end up at the force vacuum at r equal to infinity. But when you release the particle, then it will follow the equation of motion.
Yeah,
Okay?
exactly. So during the waiting time, how can I hold the particle? I mean, so it's
well,
like
this is like a construction. You can imagine that this is some field configuration in four-dimensional Euclidean spacetime that you are constructing. So you impose that this is constant, and of course, this is not a solution of the equation of motion in this constant part. But this is a field configuration that can be created by field fluctuations. Okay.
Okay. Thanks.
I will say more about the fact that these are not really proper solutions afterwards. Okay.
Yeah.
More questions on this? Okay, so we have this slope, and then you can think of these pseudo-bounces. In fact, this is just one line in an infinite dimensional space of configurations, right? In principle, you can think of these pseudo-bounces as O4 field configurations, like the bounces are, that minimize the action for a fixed value of the central field. Okay, so if you open further directions in configuration space, what you will find is that these pseudo-bounces are tracking the values that you will find in this infinite configuration space. So what I'm plotting here is taken from a real example. This is for a potential that Muhanov and company were studying at some point. And what we did was to compare their solution with the pseudo-bounce solution for this kind of potentials, which did not have a bounce. Okay, so you find in blue here, this is the track of the pseudo-bounce solutions, and in red you find the solutions that Muhanov found. I call these constraint instantons, and I will say more about constraints instanton later. But then you see the main point here is that these solutions have bigger action than the pseudo-bounces. I didn't say that this is the central value of the field at the center of the bounce. And here, this sigma is just another parameter that appears in these configurations. And then you see that for fixed values of phi, you have a slice and is minimized by the pseudo-bounces. Okay. So this guarantees that the pseudo-bounces will do the best job in finding the lowest action. Okay. So some of the properties of the pseudo-bounces, as I said, related to the question, these are not real solutions of the bounce equation, because the inner core, where the field is constant, then the left-hand side of this equation will be zero, but the slope of the potential at this particular field is not going to be zero. So this means in particular that they are not extremals of the action, but this is just fine. This is good, because what you are trying to do is just to describe a valley that is sloping away from or towards a bounce. And therefore, it cannot be described by extremals of the action. So this is fine. Okay. You can in fact calculate what is the slope of the action as you move along these valleys, and it's given by this very simple formula in terms of the radius of the core and the slope of the potential at the given field along this valley. Okay. I will give you a derivation of this later on. All right. Another good property of the pseudo-bounces is that if you take the slice, remember, these guys live in four-dimensional Euclidean spacetime, but if you take the slice at the Euclidean time equal to 0, as it happens for bounces, what you get is a three-dimensional bubble, and this is the bubble that you nucleate in the process of vacuum decay, right? Now, in order to conserve energy, this bubble has to have energy equal to 0. Remember that energy equal to 0 is the energy of the forced vacuum. And this is because otherwise you would violate energy conservation, okay? And then you can check also that these pseudo-bounces have precisely energy equal to 0, and therefore they give you a proper final state for decay, okay? Another good property that they have is that when you play this game of deforming them by multiplying the radial coordinate by a constant and having the action is stationary when you vary this constant, and this leads to this relation between the total action and the action for the gradient term. This is also satisfied by the pseudo-bounces. Okay, not just the bounces have these nice properties. Pseudo-bounces also have this property. Okay.
A quick question here.
Yes.
If they have energy 0, how do they expand? How do you get the energy for the expansion?
Well, basically, the fact that they are E equal to 0 doesn't mean that they are in a stable point. They are not in an stable point. They are. You can. If I had a blackboard, I could draw you what is the tunneling through which they are the bounces are tunneling, or the pseudo bounces are tunneling. Basically, what is happening is you start from a minimum at 0, which is the forced vacuum, 0 energy. Then you have an energy barrier that is going down beyond the E equal to 0. And it's like in quantum mechanics, in which you tunnel from this forced vacuum to the exit point. Something similar happens here. So you are tunneling from this forced vacuum at E equal to 0 to some other configuration with E equal to 0, but this E equal 0 point is in some slope that is sloping away. So once you tunnel this bubble, is not in a stable state. So it will just start expanding, okay? So as a function, if you want, as a function of the radius, okay, of the bubble, you create the bubble at some point with some fixed radius that has 0 energy to conserve energy, but otherwise the energy as a function of the radius is decreasing. So you will get down this slope if you want, okay? And so you will have, so the energy will keep conserved, but the energy, the potential energy of the bubble will be compensated by the kinetic energy of the walls. All right. So energy is conserved at all time. More questions? Okay, so these nice properties that the pseudo-bounces enjoy, I could give you some nice mathematical derivations of all of them, and you find nice cancellations between different terms that ensure that this behaves well. But at the end of the day, the reason why all this works is very simple. The origin of these good properties is due to the fact that these configurations would be proper bounces if you modify the potential in this way. So suppose you choose some particular value for the center of the bounce, and then you change the potential for larger values of the field. So you basically build the wall so that you have a minimum right at the point phi e. For this kind of potential, the configuration that I was giving you would be exactly the one given by the pseudo bounce. Okay, and this is finally the reason why these good properties hold. Okay. So let me now compare pseudo bounces with constrained instantons. These constrained instantons were proposed many years ago by Affleck to deal with cases in which there was no bounce. And these have been used very recently by Artu and collaborators just to describe forced vacuum decay when there is no bounce. Okay. So to simplify things a lot, the basic idea is that you modify the potential in order to force it to get a bounce. So suppose you look again at this potential negative quartic perturbed by a mass term that has no bounce, and then you add a higher order term with some coefficient, and then with this extra term, you can ensure that there is a bounce. Some of the drawbacks of this way of trying to get a hold on what is happening with these no bounce potentials is that the order of this polynomial is arbitrary, right? And you will get different answers depending on what order you choose for this extra operator. Another bad property, if you want, is that once you calculate the bounce, it will lead to an energy equal to 0 bubble only if this was the full potential. but we know that this extra term is not really there. So when you calculate the energy in the real potential, then you will find that this bounce has no E = 0 bubble, okay? So when you compare this with the constrained instantons, what happens, when you compare this with pseudo-bounces, then you discover that pseudo-bounces can be interpreted as one particular limit of the constrained instantons. If you remember what I just said about the pseudo-bounces being basically the solution when there is a very steep potential here, this steep rise of the potential you can actually get from a constrained instanton if you just choose the power of the extra operator to be very large. I chose n = 100 here, which is crazy, but this is just an artifact to, it's just a tool to create this pseudo-bounce profile, right? So what I'm comparing here is just different constrained instanton potentials, and I choose this parameter in the extra operator so that the bounce that I get always have an inner value that is equal to, the field is equal to 10 in some arbitrary units. So n = 6 is here, n = 100 is basically close. The minimum is very close to phi = 10. If you calculate the shape of the bounces, then you get something smooth for n = 6. For n = 100, you get something which is really very, very close to a pseudo-bounce potential, as you would expect, okay? So from this point of view, if you compare pseudo-bounces with constrained instantons, you see that the shape of this very large constrained instanton converges to a unique profile, which is the pseudo-bounce profile. And of course, now you will also get the energy equal to 0, okay? Now let me compare the actions too. What I'm plotting here for different values of n is just the action of the constrained instanton with operator n and the pseudo-bounce action. And the energy made a dimensional dividing by the energy, the potential contribution to the energy, so that I get something adimensional, okay? So you see that the energy is not 0, and the action is larger in some points, but it can go lower in others. But this is because you cannot trust this lower action for the constrained instanton because the energy is not really 0. What you have to do is you have to rescale your field configuration so that by choosing appropriately this rescaling factor, you can fix the energy. And when you do that, then you get a 0 energy, but then you see that this dip here goes away, and you always get that the constrained instantons get an action that is bigger than the pseudo-bounce action, as you would expect, because you know already that the pseudo-bounces give you the minimum of the action when you fix the value of the central, or the bounce at the center, okay? Questions on this?
Okay, quick question.
Yes.
Which kind of model can give rise to such a larger n?
No, you don't care. This is not, you are not trying to justify this from a particle physics point of view. This is just a tool to create some field configuration that approximates the one that is driving the decay in these cases, okay?
Okay, thank you.
So n = 100 is totally crazy, but it's just a way of saying that this field configuration that you get by playing this game is the pseudo-bounce configuration. That is, you will create by vacuum fluctuations anyway, because it's the one that gives the lowest action. Okay. More questions? Okay, so if not, I move to the second part of the first part, which is just what is the use of these pseudo-bounces. So some of these uses are, of course, as I already explained, you have to rely on them when you have to discuss the decay of some force vacuum for which there is no bounce. But remember, what you were doing, this trick of the waiting time was just to save undershots. And you have undershots even if you have a bounce. So you can play the same game. And this means that pseudo-bounce configuration can exist even if you have a bounce. The only trouble is that these guys are not the extremals of the action. And in particular, you expect that they will have actions which are bigger than the bounce. That's why the bounce is relevant, and the pseudo-bounces will be subleading when there is a bounce, okay? However, for some potentials, it may happen that these values that the pseudo-bounces describe may be very flat. And in situations like this, what happens is that these pseudo-bounces, they are subleading with respect to the bounce, but maybe not so much subleading. And in that case, you really have to take into account these pseudo-bounce configurations. So you have to integrate over them too, in order to estimate the rate properly. Okay. In some other cases, what might happen is that you have one of these, suppose you have a low energy effective theory, you have a potential with some minimum that falls in a region in which your field theory is not valid, okay? In a case like that, it might happen that you have access with good theoretical control for the value of pseudo-bounces, but then this value goes lower and lower and enters the region where your effective field theory is no longer valid. In cases like this, you have access to pseudo-bounces, but you don't know how to calculate properly the bounce because it's beyond the reach of your EFT. And in that case, knowing what is the action of the pseudo-bounces can be useful to get an upper bound on the action of the bounce. This is not just words, this has been actually been used by Viladoro and his collaborator recently, just precisely in this kind of setting. And in general, and this is what I will discuss next, you can use the pseudo-bounces as a tool to study the general decay structure. Okay. Before entering into this, do you have any questions about these uses?
Yes, I have a question. So when there's no proper bounce, can you prove that the pseudo-bounce always give you the minimal action, Euclidean action?
In a sense, this will be much clearer in the second part of the talk. The basic answer is yes. And when I explain the tunneling potential description of pseudo-bounces, I hope this will be crystal clear, actually.
Okay, thanks.
More questions on this? Okay, so let me just then move to the study of the general decay structure using pseudo-bounces. So before doing the general case, let me just explain what is the standard situation. Basically, in all the potentials that you probably have looked in your life, the situation will be the following. So what I'm showing here is just in a plane in which in the x-axis I have the core field value, this phi e, and in the y-axis I have the core radius of this constant core. And then what I plot here is the regions where you would have an undershot or you would have an overshot. And the line that separates undershots from overshots is, of course, the line of pseudo-bounces. Okay? This line of pseudo-bounces touches the x-axis at some point. This means no core radius, and this corresponds, therefore, to the bounce. Okay? And then it goes away, up and up. And what does it do, this line? Does it stop? No, it does not. It just has an asymptote to infinity. And the field for which the asymptote appears is just the field in which you have a degeneracy between the potential and the force vacuum. And this is clear. Below this field value, there is no way, no matter how long you wait, that the release point will end up rolling into the force vacuum, because the friction, even if it disappears, will not allow you to do that. So this explains this asymptote. Okay, you cannot go below it. And in order to get from this phi infinity to the force vacuum, then you would need that the friction goes away, and therefore you need this waiting time to be infinity. Okay, this is the explanation of the asymptote. Okay, so this is the regular situation. You just have your bounce, you have your pseudo-bounces, nice. The thing is that for some cases, this is not the full story. For some potentials, you get something richer, and this is one particular case. This comes from a potential that I was looking with Thomas Constantin, that I will show you later on. And what you have for this phi e Ri plane is you have the regular behavior that I just showed, but then you have other regions with more undershots and overshots that are separated with, by further pseudo-bounce lines. And these pseudo-bounce lines end up at the origin in some extra bounces. So this particular case has 5 bounces in total. Okay, some of these I call B-bar. These are anti-bounces that I will explain to you what they are. But in principle, you would have 5 different bounce solutions for this potential, not just one. Okay, How does this potential look like? So here it is. This is the full potential with the location of the release points for bounces and anti-bounces. It's very flat here, looks like, but if you just zoom in the origin, then you see that there is a barrier. Then it looks flat in this scale, but it's not particularly flat. So you do have this very steep fall. This corresponds to these two first bounces. Okay. So in general, it involves quite steep potentials. All right. And I will explain later on that this is needed in order to have these further structures. Okay. So what are these antibounces? So these antibounces are special in the sense that if you just use the standard searches that I was explaining at the beginning of the talk, they will miss these antibounces. And this is because of the following. Look at this normal bounce. As I said at the beginning, the codes that are used to find for them, look for them, then is that if you have an overshot, then reduce your field because the bounce will be lower. If you have an undershot, increase the field because the bounce will be for higher fields. Now look at one of these B bars. The difference with respect to that is that you have, for lower field values, you have overshots, and for higher field values, you have undershots. So if you use the usual search codes, then it will instruct the field to go lower and go away from the anti-bounce and go higher on the undershot side, and then farther away from the anti-bounce. This means that you will never converge to this solution, and the same would happen here. Okay, so this is the explanation of the name. Otherwise, if you look at the profile for these guys, it's perfectly normal. It looks like a normal bounce. So the story here is interesting in the sense that we discovered this. Thomas and I proposed some analytic potentials and analytic bounces that would be useful for people working in these kind of codes. And Maggie Muleiner, who had one of these codes, was just trying the code against our analytic potentials. And then we were given, in particular, this solution, this bounce, and she reported to us that she was finding a different bounce, but she would not find our bounce. So we were checking what was going on, and then we found that this is what was happening. She could not find it because the standard search would just miss these guys. Okay, this is the reason. If you think about this, how is this possible? You might be puzzled because usually what happens is the following. Suppose you have an undershot, okay? You have a field value that is an undershot. The rationale for increasing the field is that you release the particle from a bigger field value. This means that when it goes down again to phi e, it will reach this point with a higher value of the radius. And this means with less friction, and therefore you would improve towards an overshot instead of an undershot, right? But remember that the friction term is inversely proportional to the radius, but it's also directly proportional to the velocity of the field. So for some potentials, it may happen that even though you increase the radius, you also increase by further amount the velocity, and this can compensate the increase in R. And this is why, in order to get this kind of anti-bounce configurations, steep potentials that lead to higher slopes like this are required. Okay? Questions on these anti-bounces? Okay.
Well, maybe I have a question.
Yes. Yeah.
So this, what you described, kind of relies on solving the bounce with changing the field value, no? But,
yeah, the typical search for undershot, overshot codes.
yes, but if you have some other criterion, like to extremize the action,
Well, then you will find them, and this is precisely what we do for the tunneling potential. The tunneling potential will not be sensitive to this kind of problem. You can find them. I will describe how this is done in the tunneling potential approach.
Okay, yeah, I understand. Thank you.
More questions on this? Okay. So the general structure for the most generic potential you can think of is that you expect to have 2n plus 1 bounces within some integer. And this integer describes the number of BB bar pairs that you have, joined by pseudo-bounce lines, because remember these B lines are joined by pseudo-bounce lines to anti-B. and the same here. Okay, this just follows from the fact that these are separating overshoots from undershoots. So if this is anti, this has to be a normal one, and the other way around. Okay. So we can even say something about the relative actions of these pairs that are joined by a pseudo-bounce line, like here. Okay, I write them like B1 and B2, and rather than B and B bar, because which one is the B and which one is the B bar depends on what is the nature of this region, if it's overshots or undershots, and both can happen, as I showed before, right? So you can relate the action of one to the other just using the fact that you know how the action changes when you move along the pseudo-bounce line. So when you move from one to the other. And there is a very nice way of relating this action just using the Stokes theorem in this plane, in this area. Then you can relate the integral along this curve with an integral of a positive sign quantity inside this area. And the end result is that the action of this V2 point of bounce is smaller than the B1. Okay, so the bigger the field is, the smaller the action. Basically, this is the rule of thumb. Okay. So this we can do when the two bounces are joined by a pseudo-bounce line, but we cannot say anything definite about the relative values of the actions if the bounces are not connected by a pseudo-bounce lines. And in fact, you cannot prove that the one with higher field value is always smaller. We have cases in which this is the case, and in other cases, this is not the case. Okay, so there is no general proof of this. Typically, though, what happens is that the action tends to be lower when the field is higher. And it also happens that the highest field value in which you have a bounce is always a bounce. So the highest, here you have, for instance, the highest is a bounce, and this will always be a bounce. It cannot be an anti-bounce because you need to have overshots between the last bounce that you have and the true minimum. Okay, you cannot have undershots approaching the true minimum. Basically, this is the reason. Okay, so typically what happens is that the guy that is closer to the true minimum is the guy with the lowest action. But there is we have no proof of this, and it might well be some exception in which some anti-bounce is really the one that dominates the decay. We have no counterexample to show, but there is either no proof that the opposite will happen. Okay. Questions on this? Okay, so if not, I will just show you how the action landscape looks like in this plane. Again, we have the field value at the core, the radius of the core, and you have in this plane these usual pseudo-bounce lines that I will show you before, but now superimposed on the action itself. So you see how these pseudo-bounce lines are really tracking the values that you have in this landscape. Okay. This you don't see here very clearly because you need to zoom out, but if you zoom out, you also see that, again, this is following a valley. This green line is also following all the valleys that you have in the action landscape. Okay. So this is the last thing I want to say about the first part, and then I will move to the second. So if you have questions about this first part, I think now is the time. Okay. So if not, then I move to the second part using describing pseudo-bounces with the tunneling potential approach. Okay. So first I have to tell you what this tunneling potential formalism is. So the way we calculate the tunneling action in this formalism is the following. You look at your force vacuum, and then you draw some path out of it, okay, from the force vacuum under the barrier to some endpoint, phi e. And this path defines the function, which I call the tunneling potential. All right. So for any path like this, you can assign a number, which is this given by this functional. It's just basically an integral between the force vacuum to the endpoint of this quantity, the difference between these two functions squared, minus the slope of this guy to the cube, integrated in here. So you get a number, and then the game is change the shape of these tunneling potentials and the endpoint also, so as to minimize this functional, okay? And when you find this minimum, then you find that this minimum value that you find is precisely the same as the Euclidean tunneling action for this false vacuum. Okay, so this is an alternative way of calculating the same quantity. And the path that gives you this minimum will have an endpoint which is precisely the same as the central value of the Euclidean bounce, as you would expect, because the field range involved in the decay has to be the same no matter what formalism you use, right? Questions on this?
Yes, so
Yeah.
I got confused. So how does this time t dependence enter into the VT? I mean, is a solution? Is phi is the solution of what or something? I mean, how?
Sorry, the question
how-
was how far.
How do I get the t dependence in V of t in your
T
tunneling potential?
here means tunneling. There is no time here.
Okay, I see.
So
Okay.
it's just a way of differentiating the potential from this other function here.
Okay.
So there is no
Thanks.
time.
Okay.
More questions on this? Okay. So let me just describe some of the properties and applications of this formalism. So I introduced this function that you now have to vary, this tunneling potential. This is on the same footing as the potential, has the same dimensions. It's like they are on the same page, okay? From this point of view, the field, you don't need to deal with the field and the bounce to calculate the tunneling action. And in a sense, the field can be a distraction here. It's better just to deal with this tunneling function and the potential. And if you are interested, once you know the tunneling potential, you can always derive what is the shape of this of the bounce if you want to know. But in principle, it's not necessary. Now, one of the nice properties of this tunneling potential that minimizes the action is that it's a monotonic function, and this makes it easy to approximate numerically, okay? And this has numerical applications. Now, the key property is that the action for this tunneling potential object has to be minimized. And this is in total contrast with what happens in the Euclidean case. In the Euclidean case, the bounce is not a minimum of the Euclidean action, it's just a saddle point. And you can imagine that this difference makes the tunneling potential action very good for numerics. And is in particular useful for the multi-field case, which is much harder, as I showed with Thomas Constantin in 2018, okay? Another nice thing is that you can generalize this approach to any dimension you want. And in particular, it's kind of nice that for d equal to 1, what you recover is the formula for the WKB exponent. So if you wish, you can think of this tunneling potential formalism as a generalization of WKB to quantum field theory. This is a nice way of looking at this. Okay. Are there questions on this? Okay. So if not, let me give you an idea of how this was obtained. Okay. So in order to relate this tunneling potential to the usual Euclidean formalism, the key relation is this one that gives you tunneling potential in terms of Euclidean quantities. So if you have an Euclidean bounce, you can calculate this right-hand side. You can calculate in particular the slope of the bounce for any field value, and then you can find this as a function of the field. And this function of the field is precisely the tunneling potential. This is the link between the two formalisms, okay? So I will use this link to show you how to obtain the tunneling potential formalism, just starting from the Euclidean side. The idea is that you want to get rid of all the Euclidean quantities in terms of the potential and the tunneling potential, all right? So first, you can use this relation between the two formalisms to express the slope of the field of the bounce in terms of V and Vt. Okay, this is the simple formula here. If you take a further derivative of the slope, phi double dot, and use the chain rule, then you can show that this is just given by the difference between the slopes of the potential and the tunneling potential. Okay. You also need to get rid of the radial distance in Euclidean spacetime, and this you do just by solving the equation of motion for R. So you already know how to transform phi dot and phi double dot. You solve for R, and then you end up with this relation for the Euclidean radial distance. Again, Euclidean on the left-hand side and V and Vt on the right-hand side. If you now take an R derivative of this equation, then you end up with an equation just for V and Vt, which is simply written here, and this gives you the equation of motion for the tunneling potential. Instead of the equation of motion for the bounce, now you have an equation of motion for the tunneling potential. And then you can show that you would get exactly this equation if you vary just the action that I gave you. So the Euler-Lagrange equation for this action will reproduce precisely this equation of motion that I showed here. Okay? Questions on this? All right. So let me further show you that you would get exactly the same thing. So this is the tunneling action. You can use these equations that I wrote before that related to the two formalisms to re-express this in terms of Euclidean quantities. You change also the integral between the integration. Instead of in phi, you change the variable of integration to Euclidean radius. And you discover that what this action is calculating is just this Euclidean integral, which is nothing but 1/2 of the gradient part of the action. And as I told you already, this is precisely the total action. Okay. So in a sense, you might think that this is like a trivial rewriting of the Euclidean expression in terms of this funny tunneling potential, but it is much more than that, because if you look at this Euclidean integral, if you look for the Euler-Lagrange equation that follows from here, you don't get the bounce equation. So you cannot use this nice positive definite integral to solve your problem, not directly at least. But this is precisely what this rewriting does for you. Now you can use the variational method to solve for this tunneling potential here, and this will give you the right solution. Okay, so this means that you can also think of these tunneling potential formalisms as a variational formulation of the reduced problem. The reduced problem, this is language introduced by Coleman, is when you look at the Euclidean action in terms of this gradient term only, and you try to minimize this, fixing the tunneling potential. The action, the potential part of the action. Okay, so this is in a sense what the tunneling potential is achieving. Okay, do you have questions on this? Okay, so if not, I go ahead. So I wrote this tunneling action that one has to minimize, but if you think about it, there are basically two different variational problems that you can think of, okay? Depending on what you do with the endpoint. So if you left the endpoint free, then this is what I was telling you, that you would get the bounce solution. However, if you keep it fixed, then this is a different variational problem, and the solution will be different, and what you get basically is the pseudo-bounce, meaning the tunneling potential equivalent of the pseudo-bounce. Okay? So these are very well-defined two different problems, and these are the well-defined solutions that you get. Both of them, these solutions will be solutions of the same equation of motion. The difference between the two problems is not in the equation of motion, it's in the boundary conditions that you have to impose at this endpoint. Okay. So for the bounce, the boundary condition that you have to use is that the slope of the tunneling potential at the endpoint is given by 3/4 the slope of the potential, while for the pseudo-bounce, the boundary condition is instead that the slope has to be 0. Okay. And you see these are the two only choices. If you go back to the equation of motion, at the endpoint, T is equal to V, so this term drops. And the only way to make this combination equal to 0 is either you have the bounce boundary condition or you have the pseudo-bounce boundary condition. So in a sense, these are the two only solutions the only two type of solutions that you would expect for this minimization problem. Okay. Are there questions on this? Okay, so this is already in a sense telling you, or in a sense putting the pseudo-bounce solutions in a more firm basis. Is better motivated in this formalism, in my opinion, than in the Euclidean one, in which it looks a bit ad hoc, right? But you see that is really the solution that you're looking for is the one minimizing the action where you keep the field fixed, is really the pseudo-bounce solution. Okay. And then I'll show you that this really gives the same Euclidean bounce that the Euclidean profile that I was showing you for pseudo-bounces when you do this kind of thing. Okay. So before showing this kind of things, I will derive for you how the action changes when you change the endpoint. Okay, so let me do this in some detail here. So this is again the action for the tunneling potential. And in violet, I wrote here the dependence on the endpoint. Okay, so first you have an explicit dependence as the end of the interval of integration, of course, but then the tunneling potential also has an implicit dependence on the value of phi e, because if you change phi e, the tunneling potential solution is going to be different, right? So when you take the derivative, first you derive with respect to the boundary, and then you get the argument of the integral evaluated at the endpoint. When you vary the tunneling potential, you know what you're going to get. You're going to get the equation of motion for the tunneling potential, right? So you get the equation of motion term here, and you get an extra term, a boundary term, because when you vary the slope of Vt prime, you know that you have to integrate by parts to express it in terms of the variation of Vt, right? So you get this extra boundary term here. So the term in the center with the equation of motion you can drop because the equation of motion is satisfied, and then this will give 0. And then you have these two terms. And I'm going to rewrite these two terms in terms of the radial Euclidean distance. Okay. Remember that there was a relation between the Euclidean radial distance and the tunneling potential given by this expression. So you can, if you use this expression for the field at the endpoint, then you will find that this gives you precisely the radius of the core, which is associated with the small values of the radial distance, right? So you see from this equation here that if you want to have inner core which is non-zero, then because this quantity on the numerator goes to 0 at the endpoint, you better have a slope of the tunneling potential at phi e that it also 0. It is also 0. Okay. If this is non-zero, then the radius will be 0. So this is already telling you that, in fact, the pseudo-bounces really require this tunneling potential boundary condition. Okay. So now I'm going to replace these expressions in terms of the MV and VT, and I will express in terms of the radial distance here, the inner distance. And then you get this expression that gives the slope of the action, okay, in terms of this radial distance and the slope of the potential at the endpoint. So you get this first term that is going to be 0 anyway, because for pseudo-bounces, Ri is non-zero, but the slope is 0. And for bounces, Vt prime is non-zero, but Ri is 0, because the bounces have no inner core, okay? So you end up with this only term. And this depends on the variation of the tunneling potential as you vary phi e, but when you vary phi e, the tunneling potential at this value is just equal to the potential, and therefore this is just given by the slope of the potential itself. So I reproduce the formula that I was writing for you earlier in the talk. Okay, this is the way it arises. So any question on this derivation? Okay. So you see also from this equation that it will give you a non-zero negative slope for pseudo-bounces when this inner core radius is non-zero, but it will give you 0 for the bounces for which this Ri goes to 0. And this is just as you would expect, because you know that the bounce is an stationary point, and therefore it has 0 slope. The action has 0 slope there. Okay? All right. So these are the pseudo-bounce profiles in both formalisms. This is the Euclidean one with the waiting time Ri, and this is the tunneling potential one with the slope of this tunneling potential being 0. Okay. You can also notice that the inner core is mapped into this single point, right? Because you remember tunneling potential is potential minus the slope. The slope in the inner core is 0, and therefore Vt is equal to V. And this is this point here. You might think that this is a problem if you want to reproduce what is the action of the Euclidean pseudo-bounce using this other tunneling potential method. Because if you look at the Euclidean calculation, you find that there is a contribution to the action from this inner part, right? But remember that there is a way of rewriting the action in terms just of the gradient term, right? And this is precisely what the tunneling potential is computing. And this gradient term, both in the tunneling potential and in the Euclidean, if you rewrite the action in this way, have no contribution from this inner core, okay? And this explains why these two things at the end of the day give the same correct action, okay?
Yeah.
Questions on this?
Yeah, well, I'm really enjoying the talk, I have to say, but we're slowly approaching the
Okay,
time
thank you,
limit.
because I had no idea how I'm doing with time. So how much time I have left?
Yeah, we started a bit late, but it's like -1 minute now, I would say. So
Okay, then let me just move on to the conclusions, okay? The only thing I wanted to say...
Can I ask a question?
yes.
Yes.
If I remember correctly, so in the tunneling potential, how do we approach the real solution of the bounce is that we verify this phi e and to find the this extreme point of the action. But I just noticed that in this case, it seems the phi e is not corresponding to the extreme point of the actions. So in this case, how do we find phi e, the escape point?
Phi e, you can decide, you choose phi e and you fix it, because you have different pseudo-bounces for any value of phi e. So you have a full family of pseudo-bounces, okay? Now, when you try to minimize the potential, what you do is you fix the endpoint, but you vary the shape. And by varying the shape is that you find for the minimum. And there will be some shape that gives the minimum, and this is the pseudo-bounce for that particular value of phi e. And then you can repeat this for different values of phi e, okay?
Okay. So this is not the same strategy we used in the normal tunneling potentials.
In the normal tunneling potentials, you let phi e fixed, yes.
To verify,
Sorry,
yeah.
free to vary,
Yeah.
and that's why you find the global minimum, okay?
Yeah.
Okay. So another thing
In
I
this
wanted
case,
to say, yes?
In this case, we just let phi e to fix and
For the pseudo-bounces, phi e is fixed, yes.
Okay.
And for any value that you choose, then you will find a different pseudo-bounce solution.
Okay, thanks.
Okay. So you actually find a family of pseudo-bounces, like I was showing these plots, okay? So in green, you have the pseudo-bounce solutions. In red, below all these solutions, you have the usual bounce. And there are other solutions that you can also find, but I will not discuss because I don't have time. So let me just move to the conclusions, okay? So one of the main messages of the talk was that pseudo-bounces are tracking values of the action landscape and can be relevant even when you have even if there is a bounce. Then I tried to show that they arise very naturally in the tunneling potential formulas. They just minimize the action when you fix the endpoint. And I didn't have time to discuss this, but this formulas gives you a unified view of vacuum decay in which you have different type of solutions all coming in a family, if you want, okay? Then I showed in the applications of pseudo-bounces that in general, you expect a rich vacuum decay structure is possible with more than one bounce. And the most general case will have 2n+1 bounces with bounces and anti-bounces joined by pseudo-bounce lines. And there are some open questions still, though. One thing that we don't know for sure is how steep the potential should be to have these extra solutions. We tried to quantify it, but we did not manage to do it. And another open question is whether anti-bounces can dominate decay in some particular cases. Thank you very much for your attention.
Thank you, Jose. So, yes, I think, yeah, we still have time for some questions. Maybe Morten wrote something on chat. He's asking whether you have looked at pseudo-bounces in higher field dimensions.
Higher field dimensions or space-time dimensions?
No,
You
field.
mean
I think he's asking
multi-field?
about multi-fields.
Multi-field is something that we are starting to look into. Yeah.
Yes.
But I cannot say anything. I mean, I don't know exactly how we'll.
Zasky, if you have to somehow fix the path aside from just phi e.
Yeah, so it's a more complicated thing, but what is true is that this tunneling potential can be generalized to multi-field cases. That's what I did with Thomas. But we were looking for bounces basically, but pseudo-bounces will exist also. But I have no intuition to tell you what will happen there.
Yep. Many questions. Next one I think was Wenyuan.
Yes, so I have a question. So you gave the example minus lambda phi 4 theory plus a Maston, and to explain this does not give you bound solutions because you always have undershooting, right? And so my question is that is there any example that we cannot find bound solutions because we always have overshooting?
Yes, you can also have it. It's very simple. You modify the negative quartic with a 6 tick.
Okay, so in that case, we don't have bounds, but we still have the pseudo-bounce.
Well, you don't have pseudo-bounces. What happens in that case is that the decay is dominated by very small instantons, and basically the action is so small that first you don't trust your calculation, but you're sure that the decay is going to be so fast that you are not interested in the decay.
Yeah, so it's the solution. I mean, in that case, there's always classical solution. The real-time classical solution. It's not. The process is not timely dominated. Because I'm thinking about inflation. So if you have some potential, there's always no bound solutions. And I wonder, can we still have some certain timely processes during the evolution of the inflaton?
So I don't know for inflation in general, but I know about this kind of example in which you only have overshoots.
Okay, thanks.
Thank you. Oli, you want to go next?
My question is, if we start from a path integral, can we insert a Faddeev Popov type delta function potentially with a Jacobian to then integrate over this phi e as a kind of separate integral which we factor out, and then we find the pseudo-bounces for each phi e? Is that something that you can do, and then you can sort of see how things would generalize beyond just the exponent?
So probably, I mean, this is probably what you have to do. This is a problem that is to be solved yet. I haven't looked into it myself, but for sure you have to integrate over these values, and that would be a way of doing it. This is also connected with the discussion of R2 in his last paper with constrained instantons, in which they do a proper path integral approach for the constrained instantons. And because these pseudo-bounces are kind of a limiting case of these constrained instantons, there must be a way of applying the same things R2 is doing with constrained instantons to this limiting pseudo-bounce case. Yeah.
Thanks. And thanks more generally.
Matthias, you want to ask a question now?
Yes, thanks. Thank you for the talk. I learned a lot. And specifically, my question is about these cases where you have more than one bounce and also these anti-bounces. So you already mentioned, I think, that there's no general argument for which you know which bounce specifically will have the lowest Euclidean action, right? So I assume maybe you checked, I don't know, by computing, like do these the action of these specific solutions have a hierarchy between them, or is it simply, I don't know, order 2 or something like that? Because I wonder if the action is not hierarchical, then can it be that simply I have to keep the contributions of all of them to the decay because they will be all relevant saddle points of the Euclidean action? Well, for this particular potential, you can see it here, is dominated by this highest field value 1, which is you have a bounce here, which is quite smaller. The action is quite smaller than the rest of them. So if anything, you will have to integrate a little bit over this neighborhood of this bounce along this valley, but this is the one that is going to dominate. But this is very model dependent thing, and I'm sure you can cook up other potentials in which there is no such a large hierarchy, but I don't know. I don't think there is a general statement that I can make. Okay. Okay, thank you.
Okay, great. So I think we reached the end of the talk. So thanks, Jose. Thanks a lot. This was
Thank
a
you for the
very nice,
invitation and the questions.
wonderful talk. I really enjoyed it. Thanks.
Thank you very much.
It's
Thank
perfect
you.
into the series.
Thanks a lot.
Yes.
Well,
So
thanks.
speaking of series, we'll resume on December 11th with Peter Athron. So I
Okay.
hope to see you then.
Okay.
Yeah.
Thank you.
Thank you.